Welcome to the Dingir-Zone. Hi, I'm Victor, and today I want to talk about Pascal's wager. Pascal's wager is this mathematical statement that says that you should better believe in God because you've got nothing to lose if God doesn't exist, and if God exists, then you get infinite reward. And this is often depicted in such a matrix here, where you have two rows for whether you should believe or disbelieve, and two cases, God existing or not existing. And this is here what I was talking about. If God exists and you believe, then you get infinite gain, and if he doesn't exist, then you just have some finite loss. Okay. And disbelieving in God can cause you infinite loss when you go to hell if he existed. And this constant loss you find here on the opposite side as just some finite gain for not believing if God exists. So if you do a cost-reward calculation with that, then you will get that whatever the probability of God existing is, this multiplication with infinity will just make this part of the sum infinity, and you will still just subtract some finite number from that, so this will stay infinity. And on the other hand, the same thing happens here in this row, just with minus infinity here, plus a finite number here. The cost-reward calculation will tell you that belief is the better option in this matrix here, in this decision matrix. I'm a mathematician, and this is too primitive for me. Okay, this is very simple, and the most obvious reason why you shouldn't go by this decision matrix is that it only covers the cases that one God exists, like this, the God of the Bible. This will typically be brought forth by Christians. But what if Allah exists and God doesn't? Then believing in Yahweh then will anger Allah, and then you get even worse infinite loss. So you are just ignoring columns in this matrix here. There are just too few columns here, and that's a very simple argument against this. But again, I'm a mathematician. I wanted to know this, wanted to look at it in more detail, and because if we add a column for Allah, then you will have something like plus infinity minus infinity. Okay, infinity minus infinity is not defined, so you don't get an answer at all. Okay, and the whole concept of infinity is really much too simple in this matrix here, because in mathematics we have a much better understanding of the concept of infinity, right? This infinity is not just this one thing that people will just imagine as a very big number when you talk to them about it. So in mathematics we really have a better understanding of this term infinity. Okay, so as a mathematician, the first thing I want to have is a definition of a God, and this is a very, very big philosophical question. How do you define God? And I totally don't want to talk about that question here. I will just model God as a triple here. This is a relatively simple model, but for the purposes of this talk, this will be sufficient. So a God is a triple containing a logic formula phi, and then two things r and p. And the idea is that if you satisfy this condition phi, then you will get a reward r, and otherwise you will get the punishment p. Okay? So we don't need to talk about stuff like omniscience, omnipresence, omnipotence, omnibenevolence. That's all not part of this talk. This is just the reward and punishment under a certain condition that we need to talk about here. Okay, so in case of Pascal's wager, again, you just have reward infinity and punishment minus infinity. And yeah, a human H gets this reward, R infinity, if he satisfies the condition phi, which according to Mark 16:16 is that this human H must be baptized and he must believe. Okay? And yeah, this definition with infinity and minus infinity is how people in school might define this, because they would think that this is just the best reward you can get and the worst punishment you can get, for this simple reason that infinity plus 1 equals infinity, infinity plus infinity equals infinity, infinity times infinity equals infinity, and so on, right? This is stuff that you learn in school, and so this being the biggest thing imaginable, and this being the smallest thing imaginable, might justify to a school child that this definition makes sense. Okay. But I'm a mathematician. I studied math at a university and I wanted to go deeper. So, as someone who has been to a university and studied math, how can we look at this more closely? How can we understand this infinity and minus infinity better, so that we can talk about differences between Yahweh and Allah, for example? And yeah, the one way you can look at infinity differently is when you use cardinal numbers. And in the field of cardinal numbers, you think of numbers differently. So a number is not this abstract thing, right? It corresponds to the cardinality of a set. That's why it's called cardinal numbers. And yeah, for example, the number 0 is the size of the set of the empty set. The number 1 is the size of the set containing the empty set. Okay, this set here has one element, namely the empty set. Yeah, it's a bit confusing that there's a difference between the empty set and the set containing the empty set. Right? This set here has 0 elements, and this set here has 1 element, right? So this is a set delimited with these braces and containing this 1 element, the empty set. I think this is a bit easier when you have programmed in an object-oriented way. Then you can think of this as in terms of the type, right? You could think of this as having the type set of int, for example, and this has the type set of int. Makes sense, I hope. The number 2 is the set containing the empty set and the set containing the empty set. These are 2 elements, the empty set and the set containing the empty set. And for the number 3, it gets a bit convoluted already. Let me show you this here. The number n is always represented by the set containing all the smaller numbers than n, right? So this is what we're seeing here, right? The empty set contains all numbers, or all natural numbers, let's say, smaller than 0. There are no natural numbers smaller than 0. So that will give us the empty set. And here we have the empty set. 1 contains all the smaller numbers. What's smaller than 1? 0. So here we have the set containing the 0, so the empty set, right? 2 contains 0 and 1. 0 the empty set, and 1 the set containing the empty set, right? And yeah, this goes on now with number 3. It contains 0, 1, and 2, right? The empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. Okay. Yeah, and if you define numbers that way, then yeah, the smallest number infinity is going to be the cardinality of the set of natural numbers. Okay, and this is denoted with Aleph 0. Okay, so Aleph 0 is infinity. Now the interesting thing about cardinal numbers is that you can define sizes of your numbers more precisely. So a number x is smaller or equal to a number y if there is an injective function from the set x to the set y. So for example, if we are comparing 1 and 2, then we are comparing a set with 1 element to a set with 2 elements, the empty set and the set containing the empty set here, and just the empty set here. And yeah, in this simple case, just the identity function will do. We will map the empty set here to the empty set over here. That's an injective function. So this means that 1 is less or equal than 2. Makes sense. And yeah, this definition of less or equal then allows us to define equality by less or equal x less or equal to y and y less or equal to x. Right, this is how you can define equality of two elements, at least in case of an order that is reflexive and antisymmetric. Okay, so this is how we can define that, and this then means we need an injective function from x to y and an injective function from y to x, right? But something that you learn in first semester math is that having an injective function from y to x is the same thing as having an surjective function from x to y. And if you have an injective function from x to y and a surjective function from x to y, then you have a bijective function from x to y. Okay. And then we can use this definition to look at infinity more closely. Okay. So if we again have this Aleph 0 as the cardinality of the natural numbers, we can just keep on going with this definition of the next number. Okay, so the next number after this is again the set containing all the smaller numbers. So in case of the natural numbers, the next cardinal number, Aleph 1, then becomes the set containing the set n, right? This we want something, the next bigger thing. So so Aleph 1, the natural numbers must be in there here, but we need to also throw in all the natural numbers themselves. Okay, so this n unified with this delivers us the 0, the 1, the 2, and so on. And then we can go on with Aleph 2. We're doing the same thing again. And here we now get the natural numbers 0, 1, 2, 3, and so on. The set Aleph 0, because that's in here also, right? And then again this really starts to look like the trick we did with the empty set before. That here we now also add the number Aleph1, so the set containing the natural numbers and every natural number itself. And you can do that for eternity. Okay, so this definition of Aleph0, Aleph1, Aleph2 and so on doesn't really get us far at this point. Because, yeah, between these sets we are building, we always still have bijective functions. So we can just make this bijection between the natural numbers and Aleph1, for example, using the trick from the Hilbert Hotel. So this, we would have to map n to 0, for example, and then shift everything else. That's not a big deal. We can do that, and yeah, if we have this bijection, it means that yeah, these numbers Aleph0, Aleph1, Aleph2, they are in a way the same, right? I mean, structurally they aren't, but because we have the bijections between the sets, yeah, this is the same thing. And in layman's terms, that's what we mean when we say infinity is equal to infinity plus 1 is equal to infinity plus 2 and so on. But remember, we are working with sets here. And with sets, you can do crazier stuff than just adding yeah, a single element or two elements, right? What you can do with a set is you can construct the power set. And yeah, the power set of a set S is, yeah, the set containing all subsets of S. Okay, so for example, if you have the set 1, 2, 3, for example, then the power set would contain the empty set, the set 1, the set 2, the set 3, the set 1, 2, 1, 3, 2, 3, and 1, 2, 3. Okay. For finite sets, the size of the power set is going to be 2 to the power of the size of the set. So, for example, I just listed the elements of the power set of 1, 2, 3, and that had 8 elements because 1, 2, 3 has 3 elements, 2 to the power of 3 is 8. And yeah, the power set is so interesting in this context because there is a theorem which says that there is no bijective function from any finite or infinite set S to its power set. That's interesting because for every set you trivially can construct an injective function to its power set, right? Every element just to the set containing that element. That's trivial, but you won't get a bijective function, meaning you don't have a surjective function from any set to its power set. And yeah, in terms of the cardinal numbers, that means that yeah, the cardinality of every power set is really greater than the cardinality of the set itself. I mean, in case of finite sets, this is obvious. You take any number n, and yeah, 2 to the n is just larger than that. But yeah, again, this also works for infinite sets. Okay, there's this theorem that the power sets are always really actually larger than the sets themselves, in the sense that you cannot have a surjective function from a set to its power set. Okay, and that means that when we look at Aleph0, for example, the natural numbers, we can just take the power set of that and get a larger number. But Aleph0 was already infinite, right? So throwing the power set operator on that infinite set gives us a set that is even more infinite. Okay, And it's a different infinity. That's the interesting point. This is an actually larger infinity than this infinity, right? And you don't need to stop there. You can then apply the power set operator again, get yet another even more infinite set, the power set of the natural numbers. And you can continue with that for as long as you like. Throw more and more power set operators on it, and you will always get even more infinite sets. Okay. Yeah, sometimes you will see this expressed as 2 to the power of infinity is not equal to infinity. Okay, what does that mean for us? Well, first I want to make a definition for us to be able to compare gods. Okay, so I want to define Pascal's wager with cardinal numbers. So I will again have a god as a logic formula phi and a reward and a punishment, but R and P are sets now and not numbers, but we will think about them in terms of cardinal numbers. Okay, and then we can define a partial relation between gods by, and I will denote that with this square less than sign here. So a god G1 is, let's say, less than, or let's say less believable than a god G2 if they have the same query, the same logic formula. So under the same conditions, they will give you different rewards and different punishments, but the greater god will give you more rewards than the smaller god and threatens you with greater punishments than the smaller god. Okay, so giving you greater rewards and threatening you with greater punishment under the same circumstances makes this god greater. Yeah, and then we can define what I would call the power god. So if we have a god G who will give you reward R and punishment P under the condition phi, I will construct the power god of G as the god containing the same logical formula phi, and if you satisfy it, you will get the power set of the reward and otherwise the power set of the punishment. And as we have seen, the power set really increases the reward and the punishment. So this means that starting from any god, okay, we can use any god there is, from Yahweh or Allah or Enki or Krishna or Bumba or whoever, starting from any god, we can just always create a better god, namely the power god, who will give you more reward, more punishment. Okay, so and we can continue doing that. So starting from this god, we can get this god, but if we started at this god, we would get this god, and so on. Okay, we can just always throw another power set operator or power god operator on our gods and get a better god. Okay, and this better god then means that that you just shouldn't believe in any god, because if you take any god G, then you shouldn't believe in that god. You should rather believe in the power god of that god, right? But if you then shift to the power god, I'll just repeat the argument. You shouldn't believe in that god either, because the power god of that god is again better. So you could shift, power god operator again, you find a better god. So, and you can do that for infinity, right? You will never ever reach a best god, right? You will always be able to get to an even better god, and these gods will always supersede your god in the cost reward calculation. That's the point, right? This is this power set operator always adds an infinite number, more than an infinite factor on top. And this infinite factor will always supersede any probability, no matter how small, to supersede your God, right? And by the way, this also disproves Canterburys' ontological proof, because just in the very beginning of the ontological argument, Anselm of Canterbury just defines God as the best thing imaginable. But here we are seeing that there is no such best thing imaginable. No matter how you define that, you always just throw another power God operator on top and you always get something better. Okay, so this good, better, best relation that he uses just doesn't work, because he just says, well, I'll just take the maximum of that relation, but as we can see here, that relation has no maximum. Okay, Anselm of Canterbury was a complete amateur in mathematical logic, and he didn't even get the definition of that maximum right. So he described it in terms that would describe a maximal element, but then uses that thing as if it was a maximum element. But I don't want to get into the details, what's the difference between these two. And yeah, that's all I wanted to talk about today. Just remember, Pascal's wager is mathematically completely unsound, because this whole idea of infinity being the biggest thing imaginable is just not true. Okay, and minus infinity being the smallest thing imaginable, it's just not true. You know, in further mathematics, we have a much deeper understanding of the whole concept of infinity, and this is really a middle school, high school level of understanding of infinity. And actual mathematicians look at that and say, no, that's way too primitive, and so whatever. If you like this video, like it, share it, subscribe, and see you next time.